Alright, so in this segment we're going to study another classic problem in magnetostatics. We're going to have a look at the coaxial cable where the region between the conductors is filled with a magnetic material of magnetic susceptibility chi. Okay, so this diagram then defines our problem. Is we have a circular outer conductor. This is a circular cylindrical shell. It's not solid, so it's a pipe, a metal pipe. And then inside we have another metal pipe. Again, it's hollow. The outer metal pipe has radius b, s equals b. The inner metal pipe has radius a, s equals a. And we have a current. We're pumping a free current, total current I, down the inside conductor. Now bear in mind that this inside conductor is hollow, so all that current is flowing down the outside of this metal pipe, if you like, and it's evenly distributed around the circumference of that pipe. And let's see, yeah, the red dots here, this is our magnetic material, the red lines, and it has magnetic susceptibility chi. Okay, so we're interested in the three fields B, H, and M, and we're interested in solving for those fields in three regions. In the region inside the inner conductor, so S less than A, in the region between the conductors, and in the region outside both conductors. Okay, and our approach is going to be to use, we're going to straight away apply Ampere's law for H. This is the easiest way to solve a problem of this kind. And it really illustrates the utility of using H. So we're going to use this form of Ampere's law. Okay, so bear in mind what this law says. It says that the integral of H dot dl around a closed loop is equal to the free current enclosed by the loop. Now the only free current in the problem is the current that we're pumping down here, down the inner conductor. We can have bound currents in the magnetic material, okay, either bound volume currents or bound surface currents, and they will play a role, as we'll see. But Ampere's law for H responds only to the free current crossing the loop. We're going to use the following coordinate system. Okay, so the z hat direction is going to be in this direction, the phi hat direction like this, and with that choice for a right-handed coordinate system, s hat points outwards from the cylindrical axis. Okay, so let's proceed to calculate using this equation. So we'll approach first of all the region S less than A. Now for S less than A, it's a particularly straightforward problem because the closed free current is zero. That's the first observation. Second observation is that from symmetry, if the fields exist, they have to be in the phi hat direction. All right, so quite clearly then, from those two pieces of information, inside the inner conductor, since the enclosed free current is going to be zero, if I draw a little circular loop inside here, no current crosses it, that combined with symmetry tells me H is zero. Since there's no magnetic material, M must be zero, and therefore B must be zero. So in the region inside the inner conductor, we have the simple situation that for A less than S less than B, all three fields are zero. All right, first straightforward result. Okay, so let's now go to the more interesting case where we're going to look between the two conductors. Let's have a look in there. And of course, in that case, so between the two conductors, in that case, the integral of H dot dl is non-zero because the free current is non-zero. In fact, the free current enclosed is going to be I. Now, the loop that is the current we're putting down the inside conductor. The loop that we're going to draw to solve Ampere's problem here is going to be a circle, and a circle of radius s. And because we know H is in the phi hat direction, the integral of H dot dl becomes simply 2 pi sh is equal to I. And this combined with symmetry gives us that H is equal to I on 2 pi s phi hat. All right, so there is our equation for H in this region. Okay, straight away we can extract our calculation or the value for M, because we know that M is given by chi H. Alright, so there is M in the region A less than S less than B, and all we need now for this region is to calculate B. Alright, so there is our equation for B. Now what you'll notice in B is that B is different from H. It's different in this trivial way, that there's a constant mu naught out the front, but more importantly there's this extra piece of the current, chi I, over and above the free current, which is this 1 times I. Now, of course, this is bound current, and the question is, where is that bound current? Is it bound volume current, or is it a bound surface current? And in fact, this is a bound surface current, and it's a bound surface current at the radius of the inner conductor, and we can show that in a very straightforward way. Let's calculate the bound surface current density at the inner conductor. Alright, so this is what you'll find. Now, of course, the outward pointing unit vector in this case, so let's be careful here, this outward pointing vector is in the minus s hat direction. Right? The outward normal is defined as the normal as you move away from the magnetic material. At this inner surface, that's going inwards towards the cylindrical axis, towards s equals 0. This gives us a surface current density at that inner conductor in the magnetic material in the positive z hat direction. Now, to get the total bound surface current at the inner conductor, we have to multiply by the circumference of the inner conductor, which is multiplying by 2 pi a. This gives us the total current. If we multiply by 2 pi a, we just get chi I, and that's precisely this chi I that appears here. If you were to calculate the bound volume current in the region inside our Amperian loop, I encourage you to go and do this. Go and calculate the curl of M, and with M calculated earlier, and you'll find that this is 0. So in other words, all the bound currents here that matter, all the non-zero bound currents here are bound surface currents, not bound volume currents. We now need to look at the fields in the region S greater than B. And alright, so once again in this region, let's calculate H. Once again, the free enclosed current is I, the current that we're putting down the inside conductor, the one at S equals A. It's the only free current in the problem. And so we wind up with the same result as we had between the cylinders. Okay, but outside the two conductors, we also have M is equal to 0. M is 0 because there's no magnetic material out there. So in this case, the B field is equal to the H field up to mu naught, of course. So the B field now is going to be the following. And those are our results. Those are our results in the region outside the coaxial cable. Now you might look at the equation for B and you might ask, well, why doesn't the bound current at the surface of the inner conductor contribute to be outside the coaxial cable? After all, it does cut that Amperian loop, and the reason is that we now have two contributions from bound currents. One is a bound current flowing in the z hat direction along the inner conductor, but the other one is a current of exactly the same magnitude flowing backwards, back in the minus z hat direction along the outer conductor. And we can see that in the following way. Let's have a look at those two bound surface currents. Alright, so if you do the calculations for K, this is what you'll get. We calculated this one on the previous page, and we found that we get this bound surface current density chi I on 2 pi a z hat. If you do the same procedure at the outer conductor, you'll wind up with this equation. You might ask, where does the change in sign come from? Well, the change in sign comes from the fact that the unit outward, the outward pointing normal at s equals b points in the plus s hat direction, and here at s equals a it points in the minus hat direction. If you multiply this by 2 pi a, the circumference of that inner conductor, you get the total bound surface current, and you get chi I, and if you multiply this by 2 pi b, you get minus chi I. And so these two contributions cancel, which is why b outside the conductors has no contribution from the bound surface currents. All right, so let's write a summary of our results. Alright, so this is what we've discovered. We know that inside the conductors, we know that all three fields are equal to 0. Alright, so this is what we've discovered. Inside the inner conductor, all three fields are equal to 0. In the region between the conductors and outside the conductors, H is the same. Outside both conductors, M is 0 because there's no magnetic material, but M is non-zero. And it's this non-zero M which contributes to the extra term here in B. This is the bound surface current term at the inner conductor. Outside the two, there is no, we get no contribution from bound surface currents, but that's because we have equal and opposite currents flowing down the inner and the outer conductor.